Our speakers this evening have a combined, holy cow, 60 plus years of industry experience. I kid you not, 6-0.
I'm 55 of those.
That's a great answer. To my right, starting from my closest right, Art Anderson is a senior developer and experienced engineer at Aerospike with over a decade of experience. The next guy in the center is Tim Faulkes. Am I saying your name right?
Yeah.
Okay, Tim Faulkes, chief developer advocate for Aerospike with over 30 years of IT experience. And to the far right, to my far right, your far left, is Srinivasan. He is the founder and CTO of Aerospike. He's also the inventor of dozens of patents in database and distributed systems technologies, with over 20 years of designing high-scale, real-time infrastructure. His prior role included being on the team at IBM that invented DB2. Welcome to the Aerospike team.
Thank you. All right, thank you. And that's a hard act to follow. So we're going to talk about vectors. We're going to talk about AI. I'm going to assume you know nothing about vectors. If you're an expert in vectors, you might be bored at the start. Hopefully we'll tell you some interesting stuff at the end. If you're new to vectors, then you're where we were not long ago. So the aim of this is to educate, have fun, ask questions, heckle. I'm aware that I have a nasty Australian accent. If you can't understand me, please yell or shout and say, "What did you just say? I can't understand you." Throw something soft, preferably, at me, and I will slow down. I know I get excited as I talk about Aerospike and vectors and all sorts of things. So if you have questions, ask as we go through. If they're going to take too long, I'll defer to the end. We'll talk afterwards. All right, so put your hand up if you consider yourself an AI expert. Okay, good, that eliminates that heckling. Who's heard of vectors? Okay, who knows how they work? Who knows what they are? A few people. Okay, good. Most of you will stay awake for this part, that's good. So let's talk about vectors. Everyone's heard of them. We all know about ChatGPT and all these fun things that store data. A vector database is a critical part of most AI pipelines these days, and we'll cover why. And they fundamentally do two things. They store information and they allow us to do searching. And obviously, almost all databases allow us to do searching. So what's novel about this? Most databases do an exact search. So I can look up Tim and I will find only the records that contain Tim. But a vector database has a similarity search. It says, well, maybe Jim or Kim is close to Tim, so maybe you really want Jim and Kim. And we'll come to cases where that becomes very useful. And so there's all sorts of different reasons why we want to do this.
I know what vectors are, sorry.
So say again?
No, I just remember where they are now. They make it easy to search specific keywords, right?
Similarity search, we'll cover it. Okay? Now, when you start talking about vectors and vector databases, it's like you've entered a foreign language. It's like you're trying to talk Swahili or some odd language. And you come across a whole bunch of acronyms. So I'm going to tell you a bit about them very quickly. A vector is just a fancy term for an array of floating point numbers.
Will this be available like
If you're bright us enough. Yeah. Eric, can we make the slides available later? He ran. We'll answer that, but yes, it should be. All right, so a vector is just an array. It's a fancy term for an array of floating point numbers. A dimension is how many numbers are there in your vector. So I've got 0, 1, 2, 3, 4. That has a dimension of 5 because there's 5 numbers in that. And semantic search, as we mentioned, has it's a search, but it's searching for looking for meaning as opposed to trying to find an exact match. So imagine you've got a picture and you're trying to find a picture that's closest to that. You're not looking for that exact picture. That is a semantic search. So it's finding the meaning across it. And we'll cover some use cases where this comes useful shortly. Now, then you're going to find a whole bunch of other acronyms. You don't need to know these, but you'll hear us talk about them. So the first one is a KNN. So effectively, imagine you've got a million vectors, and you want to find the vector that is closest to the one you care about. You might not just want one, you might want the 10 closest. So that's a KNN. I want K nearest neighbours. Okay, K in that case was 10. This is an approximation most of the time. It doesn't mean there might be 20 that are really close, and you don't really care which 10 you get out of those 20. They're close enough that it doesn't really matter. It's an approximation. And that means that it's, sorry, my bad, I've moved on. The KNN is an exact match. It says, I really want just those 10 closest ones. The next term is an ANN. It's an approximate nearest neighbour. It doesn't have to go and look at every vector. It says, oh, I've got 10 out of the 20. They're pretty close. That's good enough. It's much lighter computationally, and the results are typically about the same. One term you're going to get sick of me hearing is HNSW. This complex algorithm is a hierarchical, navigatable, small world, and it's something we'll talk a lot more about. Everyone heard of LLMs? Okay? So we all know that's large language models popularized through things like ChatGPT and so on. It's a way of performing natural language tasks. And RAG is what we're really going to be talking about. These are retrieval augmented generation. I'll cover that in a lot more detail too. Now, just to confuse, because everyone's heard the NN of the KNN and the ANN, CNNs are also sort of part of the AI system. They're used to form LLMs, so they're not really part of a vector database. All right, so let's talk more about vectors. I want to do a semantic search. So I've got a set of inputs, and these can be text, they can be video, they can be pictures, they can be audio, they can be in almost any format. And you want to be able to search for meaning across those. So what you really do is you take your sources and you run them through a model. And those models embed it, and they turn that into a series of numbers, those vectors we talked about. Now I've shown a simple example with 5 dimensions here. In reality, a complex vector might have hundreds or thousands of different numbers there. So it's way bigger than what I'm showing. I'm trying to keep this nice and simple. All right, now, about several months ago, I knew nothing about vectors. This was magic. It's like, well, how do I do it? I've seen those demos where you have like 30 different images and you say, here's my image, which one's it closest to, and I'll magically pick the one. So what I want to do now is go through fairly quickly an example of this. It's a trivial example, but it's one that makes sense. So let's say we're buying a house. We want a house that's about 2,500 square feet, and we want about 6,500 square feet of land area. To us, floor space is twice as important as land area. There are 9 houses in my neighbourhood for sale. Which one should I buy? And I've sort of got some different land areas, I've got different floor areas, and I've got a plot on them. Now, this has introduced a couple of concepts. I've got a set of information, and I want to find not an exact match, I want to find something that is close to it. It's also got a weighting. My land area is floor space is twice as important as my land area. So I'll come back to that in a moment. So, my vectors here have 2 dimensions. They have a weighted land and a weighted floor. And what I did was I took this information and I normalized it. I said I'm going to divide all my land areas by the largest land area. I'm going to divide my floor area by my biggest floor area. And so you can see this one gave me a normalized land area of 1. This one gave me a normalized floor area of 1. All the rest are less than 1. So all my numbers became from 0 to 1. Became a nice simple vector. And then I applied my weightings of half. You can see my normalized land now is half the values they were before. So all I did was I performed a mathematical operation and turned these into a series of numbers. Now, I have my house I care about. I wanted 6,500 square feet of land, and I wanted 2,500 square feet of floor space. So what I did was then I took the same algorithm and I applied that onto my desired search vector. And this gave me my vector. So what I now want to do is find, out of those 9 houses, which one is closest to that. Now there's a couple of different ways we can do this. There's a couple of different algorithms. You can use cosine similarity, you can use utility and distance. The one I'm going to use is cosine similarity. Now, it's a big fancy name. It's a really simple formula. It's just the dot product of the 2 vectors divided by the magnitude of those 2 vectors multiplied together. So when you start hearing these terms like Euclidean distance and vector space and cosine similarity, Don't get scared, it's really just simple maths. So, this is a very easy formula to calculate. I've got 2 vectors, and I can apply that onto each. This is the code that I could do it on any size vector. I'm not going to go through it. But you can see the code's really easy. So, now that I've got my desired vector, I can go through for each one of these 9 vectors and look at the distance, or using that formula, of this vector with the vector that I want to match, and I get a similarity score. Now, a cosine similarity gives me a number between -1 and 1. The closer to 1 it is, the better the match. So the one which gave me the best match was this 0.994. And so the one I would pick was this house. That gave me the best result for what I was looking for. Does that example make sense? It's a very simple 2-dimensional vector. So my dimensions are only 2. And as I said, a real vector has hundreds or thousands of dimensions. But it's a real life problem, and it shows you how these sort of searches work. I'm not looking for an exact match. I'm looking for something that has the right meaning. All right. In a real world, if I was buying a house, I wouldn't just use those 2 dimensions. I would add number of rooms, number of toilets, number of quality of the neighborhood, the age of the house, and so on. You'd increase the dimensionality to get better accurate results on what you're actually searching for. And that's the process of vectors. I also normalize my vectors in the range of 0 to 1. That's not a requirement. You can use whatever floating points you want. The one thing that is key, when I created my vectors, I applied an algorithm onto my source, and I stored those vectors against each record. Then I took my desired thing and I applied the same algorithm. So when you're transforming your data into a vector, you must use the same algorithm on that transformation of your input as you did when you transformed the data. Otherwise, the results will be meaningless. All right. Any questions on that? Either I'm doing a great job or you're all fast asleep. Put your hands up if you're fast asleep. Okay, one gentleman, that's okay, good. All right, so HNSWs. We had a big debate earlier whether this was a hierarchical navigatable small worlds or hierarchical navigatable small world. So if I've made it interchangeable, just pretend that they're consistent. I don't care which way because the jury's out on that. All right, so the HNSW is a very fancy algorithm. Our example worked well because our vector space was trivial. It had 9 vectors in. Imagine we had 1 million, 1 billion, or even 1 trillion vectors. An Aerospike will quite happily store 1 trillion vectors. The problem is with that algorithm, I had to compare my result against every single vector. Worked well with 9, it wouldn't work well with trillions. Then I had to sort the results. Again, problems. Okay? So what we're trying to do is find a better way of solving this problem. We don't have infinite compute resource and we don't have infinite compute time, so we want this to be fast. So when I was doing some research on HNSWs, I came across this concept of a skip list. And a skip list is very similar to how an HNSW works. Imagine I have a set of numbers, and I want to insert 225 in this list. It's not a binary tree, it's just a linked list of numbers. Well, what I can do is I can store my lowest level as a linked list. But every so often, I'm going to have a higher level. So basically, it's a random chance of I'm going to go up a level. And so you can see, as I go up the stack, I have fewer entries. I know where these are, and I can do a jump between these entries, and then I can get more and more refined as I go down the stack. So if I'm looking, for example, element 225, I'll start at my head, and I'll go down. Then I compare my next element to say, is my next element 237 greater or less than 225? No, it's less than, so I stay there. In this case, I now compare my next element, 68, and say, yes, that's less than, so I'm going to go across and then go down. And we repeat that algorithm, going across and down, until we find the right answer. So my answer says it's going to be after 221. So this is a probabilistic skip list. It's a very simple algorithm. And now when we talk about an HNSW, we're going to extend this concept from 1 dimension to n, where n is the cardinality of your vectors. So that concept of I've got different levels of information. My higher levels have less information, it's less exact, but I can traverse across that graph much faster. As I go down, I get more specific. So effectively, I take one point, I find the closest point at the high level, and then I drop down. This is more specific, I have more data points here, and then I extend, go down until I can find a small neighborhood, a world that contains my small neighborhood, and then I can search within that. So it's a very efficient way of traversing a very, very large data space. And the bigger your data space, probably the more layers you've got. Does that make sense? Okay, now the key point here is it's a simple algorithm, but one lookup in a trillion record or billion record graph can take lots and lots of data points to retrieve off the database. It can take thousands, literally thousands of lookups on these data points. And so you want to make this very, very fast. So Aerospike has an algorithm that works on top of the Aerospike database. Now, Aerospike is a very scalable key value database. So our storage layer is our scalable key value database. This is a data layer that is designed to go up to petabytes of information. It goes from megabytes or gigabytes up to petabytes. And each lookup is very, very fast. We've got customers in production where every lookup on this database is about 250 microseconds, and that's off storage. So we've got a very flexible, powerful layer, and what we did was we took that and we implemented an HNSW index on top of it. So imagine this is an extraordinarily fast, extraordinarily scalable data layer. This layer is going to contain that algorithm we just spoke about, the HNSW. It's partitioned, it's horizontally scalable, so that I can add more compute nodes, I can add more scale here, and it will just work. It also distributes the data geometrically. So if I imagine my data space is a cube, I've got 3 nodes, it might slice them horizontally. And so each one of the nodes in this area processes a different part of the algorithm. And so they communicate with each other, but it's scalable, and it means that my client also knows which part of the algorithm to go to find what it needs. It's also really clever. I was speaking to our engineers about this, and imagine we're storing fraud, credit card transactions. We're looking for fraud. We've got 1 million good transactions and 5 bad ones. Those 1 million good ones all sort of look the same. So they're going to be operating in the same part of that vector space. The bad ones are probably going to be scattered around the outside. Well, that works well, but almost all the good transactions will be good. They'll be hitting the same node because it's good. But the algorithm here is actually intelligent. It says, well, I've got a lot of load on that one node because that's where my common vectors are. I'm going to replicate that across the other nodes as well. And so the high frequency transactions get faster and faster over time because you've got more and more nodes that can handle that load. All right. So these algorithms work well. There's one problem with this. Reads are really good. We've spoken about how they work on the reads. It's a nice, simple algorithm. What about writes? If you think back to that skip list, I've got a whole bunch of interconnected nodes. If I'm doing 2 writes in parallel, what happens? They're going to conflict with each other. They have to insert different information into the same object. So there's a couple of ways of solving this. The first is you can put a lock there. And then when I do multiple writes, they queue behind the lock. I only do 1 write at a time, and I don't have any contention. It means that everything's really nice and stable. What's the problem? Who said that? It's really slow. Okay? This is great if you've got really low throughput, but it doesn't work real in production situations. So we want to remove that lock. It's bad. We don't like blocks. So we're going to let everyone go freeform on their HNSW. The problem here is that we're getting conflicts. Our index will get corrupted over time. These things will fight with each other. So this is a well-known problem in HNSWs. So we came up with a solution. We patented, and what effectively you do, let's say we're inserting 1 million writes into an HNSW. Well, we can't serialize them, it's too slow. We can't do them in parallel. So what we're going to do is we're going to batch them up. And each node, remember I said these nodes know about a particular part of that vector space? Each node will form its own local HNSW of 1,000 of those, let's say. And then it will obtain one lock and merge that subtree, that local HNSW, with the main HNSW. And that removes a lot of the lock contention. It allows a lot of parallelization, and it gives really good performance on writes as well as reads. The one drawback of this algorithm is there's a bit of time taken to get those 1,000 writes, form your HNSW, and push them in. And so if you do a write and straight away do a read, your results might not be there. It takes a little bit of time to get that. In real world scenarios, most vector databases are very, very read heavy. If it takes a few seconds to get a write through, it doesn't really matter. All right. Any questions so far? Everyone with me?
What is that?
So when you write into them, you write into one server and then there are read replicas that copy the data from the right servers, or how does it work? The last step.
Yeah.
After the lock.
Yeah, so this is effectively, we don't need read replicas, so effectively one of these will process multiple reads in parallel. So I've got lots of, each one of these will process a section of that HNSW. And so anything that's in that section of the HNSW will go to that one server. As I said, if that server gets too heavy, there's lots of transactions go to that one, it will then automatically replicate that to the other servers, and then you'll get that parallel reads. So it's a deterministic geometric cache.
So from a cap theorem standpoint, it will be eventually consistent but not immediately consistent.
On the writes, yes.
Got it.
Correct. So
like, is that saving time when it comes to getting the data, this new solution?
the reading is the easy part. Okay, so this geometric cache solves that reading part. The hard part is doing the inserts, but as I said, if you're doing lots of reads, then we'll scale this cache as necessary, so the parts that are really hot will get replicated between the different nodes in the cluster. And you can scale this computer if you're saying, if you find that one node or a set of nodes are particularly hot, then you can just scale the cluster.
Are we writing to the different nodes or?
Yes, your algorithm, the implementation will go and write to the different nodes itself. So the client actually knows, I'm going to talk to this part of the graph, and it'll go to the right node, which will service that part of the graph. And so it's trying to minimize network hops and network contention. It will then do a read from that local part, or if it's doing a write, it'll write into that subtree, and then eventually that will get merged into the main tree. So.
And you're not representing the storage layer here. This is the vector layer. There's something, another, off to the right is your storage and not visible.
Yes, very correct. So this is your storage layer. I'm looking at this, but fundamentally this is a cache. If this went away, we've got everything, we can rebuild it off the storage tier. And remember, this storage tier is very fast. It's not as fast as memory that we're doing this in, but it's still very fast and very scalable. Great questions. Anything else? All right. So, there's all sorts of different reasons we have a multi-model database. So Aerospike can store key value, it can store graph, and it can store vector. And the common question we hear is, why do I need all of them? Why can't I just use a vector database? Why can't I just use a graph database? Okay, so let me address that in a moment. The first thing I'd like to say is, Aerospike started as a key value database. We've got a lot of customers out in production who have information stored in key value databases. If they want, a vector augments existing data. So let's say I've got a customer record. It's got 1,000 different fields of names, ages, and so on, and I want to vectorize it. I can just add extra columns onto that and put in the vectors. So vectors augment your existing data. A vector has no semantic meaning in its own right. Okay, that's like, imagine a vector being like a lossy JPEG compression image. And you've compressed it down far enough that it doesn't actually mean anything. It's undoable. You can't get that information back. The vector allows you to find existing records that have other semantic meaning in their own right. So, why do we need all these different types? Well, what is a vector? A vector is it's useful for semantic search. Vectors themselves have no intrinsic meaning. A vector database typically does not store relationships between different records. Now, we're all used to SQL databases where you've got foreign keys and key value databases where you store relationships between. And it augments existing objects. Now,
So do you have to have a vector for every, well, not for every, but let's say you had several columns, would you need a vector for the columns that, for each column that you felt was important, or could one vector cover several columns?
That's a great question. So you could do that. More normally though, what you're trying to do is find meaning across a set of information. So typically each row would have one vector. So imagine a credit card transaction. I'm looking for fraud. You wouldn't just encode the amount as a vector. You'd take the entire set of the amount, where it's performed, who performed at the terminal, all that information, and you turn that into one vector. So it'd be a high dimensionality vector. So it'd be rare to put a vector on a single column. It's more a set of information that has logical coherence for you.
Is there a standard, or each customer would have to decide?
It depends what you're trying to do. And most normally what we've seen is one database record becomes one vector. Now you might have two different algorithms that encode them. So your large language models, and we'll cover this in a moment, takes your object, so your credit card transaction, and vectorizes it in some way. When I want to search for that same thing, it'll apply the same algorithm and vectorize what I'm searching for as well. So if I've got two different algorithms that are encoding the same object in different ways, I'd have two different vector columns. And when I go and look it up, I'll say I want to use that vector, I want to use that vector. So the algorithm defines what the inputs are and what the vector will look like.
The vector, though, is an array, right?
Mm-hmm.
So you could maybe think of it as each column is one of the values in the array.
Potentially. That's a very simple encoding. So yeah, in my example, the house prices, each column was a part of the vector. And I could extend that. But as we start talking about LLMs, imagine we're looking at images. We've got a database that has 1 billion images, and we've got to upload a photo of a dog. Which one is it closest to? Well, that depends on a whole bunch of information in the image. And so you get these models that are open source, which will encode those images and turn them into vectors. And you can say, I want 512 dimensions on this vector. And it will store that against each image. When you do the vector search, you take your search image and you encode it with the 512 into 512 numbers, and then it'll compare those vectors. So it may be columns, but it's probably more general than that.
So just one thing to be cognizant of with the way that this works is a vector is stored in a bin in a record in Aerospike, right? So a column in Aerospike. And when you are setting up the vector search, you are creating an index on that specific column. So if I had multiple columns within a record that were all storing vectors, I would have individual indexes for each of those different columns. So I could do a vector search on one of the columns within there, but I'd have to use a different index to do it on the second one. So it's generally lighter to have a kind of a one vector capturing the semantic meaning of everything that you need within that record, if that makes more sense.
And just when you do a call out to OpenAI, you get your embedding, you're getting a vector back, and so that becomes a singular representation of that piece of content you submit.
Yeah, actually, let me jump ahead to a slide which might make more sense. All right. So we're all familiar with LLMs, right? So we've all heard of ChatGPT and Bing Copilot, things like that. So effectively what these do is they take your query and they run it through a model and they get a result. Those models have been pre-trained against a huge data set. Okay? So they work really well. So you can go into ChatGPT and you can say to Aerospike, how do I create a secondary index in Aerospike? And it'll give you an answer. Now the problem is that these answers have three problems. One is they're trained on a specific data set at a point in time. What if my information occurred after that point in time? So let's say the vectors were trained at the start of 2023 and something occurred in the start of 2024 and I asked about that. It has no knowledge of that whatsoever. And so it might make something up. And so that data gets stale, the models get stale over time. They're not domain specific. If I want something that is specific to Aerospike, I can't give it that because it doesn't know anything about Aerospike when it got trained. And the other one is it's really prone to hallucinations. If it doesn't know the right information, it's going to come out and say indexes Aerospike are created using the secondary index administration tool. There is no secondary index administration tool, and there never has been. So this is a pure work of fiction. We've all seen hallucinations done by these vectors. So what normally happens when you use a vector database? We have an embedding model. Now this is a natural language query. At some point it needs to be turned into something a machine understands. You and I understand this. A computer doesn't. It understands ones and zeros. You know, we've gone a long way, but it still needs ones and zeros. And so this embedding model takes this information and turns it into a vector. That vector has semantic meaning. It stores those in a vector database. Now, when I go and ask it my question, so it's encoded a whole bunch of information. This vector database might have got your reference documents. So let's say we went and scraped the Aerospike website, we turned each document or each section of a document into a vector using the same embedding model. When I go and ask it a question, it will take my English and turn it into a vector. And then it will say, right, I've got a million different vectors, which ones are closest? Which ones have the closest semantic meaning to what Tim is asking about? And it will find those documents, technically, it finds the vectors, and then it loads the records associated with those vectors. Remember, these vectors themselves have no meaning to us. We can't decode a vector, it's lost the information. But we associate it with a record. We put an extra column on a database row to say, hey, this is what we mean, this is our vector. We're going to load the closest one, and we'll turn the information, the semantic information, into context. And this allows the LLM from the engineering prompt to take that context and turn it back into English. So it comes by this, gets information, turns it to an LLM, and gives us information that is accurate. It removes those faults in the untrained models, because I can add recent information, I can give it domain-specific information, and I give it enough context that it doesn't need to hallucinate anymore. It knows the answer instead of just making them up. Does that help?
Incidentally, GPT-4o actually provides the right answer now, as it seems.
Yeah.
On this particular one? Yeah, but this is unfair. I actually made this example up because Aerospike's been around long enough that it knew about it.
Okay.
So yeah, I cheated. All right, does this help? Okay, because vectors aren't magic. They're just an extra column on your data set. It's looking them up. It's a different way of looking things up. It's a semantic search rather than an exact search. Okay, and you can embed whatever menu you want. If you go into huggingface.com, there are literally 300,000 open source models that do these parts for you. Okay, you can transform almost anything into almost anything you want. You can take text and turn it into an image and so on. To get the context, you need that vector database. Okay. Any questions on this? Does that help? All right, so let me just go back on this quickly. Why did we need multi-model? So Art is going to show you a demo he built. This is a retail website. And effectively, imagine Amazon or whichever your favorite retail website is. You click on a product and it shows you some information about the product. And then it says, okay, here's some other things that might be useful. So here's things that people have bought who also bought this product. I might not want to click on a product. I might want to say, show me anything that has a red hat and butterflies on it. And it will search. So when I clicked on the product, I went and got the product information. That is a key value access. It's a traditional database read. When I said, show me similar items to this item, or I said, enter the red hat, show me a red hat with butterflies on it, that is a semantic search. It's taking English or a product and finding closest things to it. So I'm using a vector database. When I want to know who has bought this and what else did they buy, that's not a semantic search. We want an exact match. That's traversing a graph. So we'd have products and they'll be purchased by customers. We want to find, for the customers who bought this product, what else did they buy? So in this one web page, I'm using all three different sorts of databases. They all have different meanings and different reasons for existing in your ecosystem. You'd almost never use a vector search database only. Okay, you'd always combine it with something else. Skip these ones. All right, so there are different sorts of databases. Some, I'm sure people have heard of things like Pinecone. There are some very specific databases that have one purpose. It's a single model database. So Pinecone is a vector database. Single model databases are optimized for a particular model. They don't have to worry about being general purpose or anything like that. As a result, they tend to be up to date. They have more features that are specific to that one model, and they can be faster. They're not necessarily, but they can be faster than a general purpose database. Multi-model databases allow you to use all three different things, like we just showed. So Aerospike is a multi-model database. It supports key value, graph, and vector. It allows you to interop between the database. I can have one copy of my data. If I'm using 3 different multi-model databases for the same application, I probably have 3 copies of my data. I have 3 times as many servers, 3 times as much data to manipulate. So these are easier. They might not have the latest features, but they do feature better integration between the different hardware models. All right, I went through that. All right, are there any questions on this before I hand over to Srini?
What kind of AI? Can you use ChatGPT or something?
I'm going to wait until Art shows you his demo, and then he'll explain the architecture and what we're going through that. It's a great question, don't apologize. We're using some of the open source models off Hugging Face, so things like Gemma and Llama 4 and stuff like that, but Art will give you the details of what we're doing.
Sorry.
Don't apologize, great questions.
How does the search work on when we have multiple indexes?
Multiple indexes?
Multiple indexes on the search.
Okay, so the question was, how do searches work when you have multiple indexes? With a vector database, as Art said, you can put multiple different vectors on which have different meanings, but when you're searching, you know which one of those vectors you want to look for. So it has semantic meanings based on that. It depends on your use case, but you'll typically know what that is.
Okay.
It's not like an index on a database column. Remember that your whole record will typically become one vector.
But if you have 3 pivots, I'm searching on one search criteria, then one more.
Yeah. Yeah, you might say, well, I know when I encoded this, I encoded it with this model which solves this use case. And that vector is this vector here. I will use that vector to go and solve the problem. Okay?
One vector would solve 3 features?
No. Well, it depends what you're trying to do. It's a very generic question. So if you've got 3 very different use cases, you might have 3 different models. You have 3 vectors, but when you're applying the model, you know what problem you're trying to solve then, and you know which of those 3 vectors would be the right one to pick.
Okay.
And the client knows which partition, if you will, to go looking at.
Yeah, and that's transparent to your application. Yeah, all it needs to know is, hey, I created a vector called Bob, and it's in this column. Go and use that, and then the vector database will take care of the rest.
Wouldn't that increase the latency of the search results?
Not particularly. We'll talk about the latency when we show you the demo, because it's surprisingly fast, depending on how it's implemented.
Okay, so I'm going to not take too much time, but I'm going to talk about the systems aspects of things, why you should care that vectors work in the Aerospike platform. What I'm showing here is essentially how the Aerospike data platform is architected. I have given talks here before, and we've talked about the storage engines, we've talked about the real-time data services. So I'm not going to repeat those. There's a lot of information, both in terms of papers, in terms of our documentation, and so on. The basic concepts that I want you to understand, or at least remember, is that Aerospike has certain technology we've invented over 15 years ago called hybrid memory architecture, where we leverage SSDs for storing real-time data. This creates certain benefits in terms of being much better at scale applications which are real-time. Okay, and then that's something which is in fact, the folks that Alex has left, but he's been using it for over 10 years, for example, in various companies. There are many companies in New York which use us. On top of that, and so we work with all kinds of storage, pure in memory, our own hybrid memory, combining DRAM and SSD and pure flash. Okay. And then we have a whole bunch of real-time processing that we do on top of it. We're written in C. We talked about it. Eric had the question. It's a high performance. It's got great, CPU, networking, and other kinds of technology. But the most interesting thing is we bring all of the benefits which run on any cloud actually, on-prem and all clouds. We bring it to various data models. And we also work with a bunch of connectors, on the real-time side, as well as in terms of querying, using Spark, for SQL, Elasticsearch, and so on. So why is this interesting? It's interesting because if you're already using our platform for high-scale applications, or if you've never used the platform at all, then when you are actually building out a vector database search or a graph API application, you're going to be able to scale it to large workloads. That's what you get out of this, okay? And that's the main reason it is there. So we now support graph and vector along with the NoSQL concept of key value and document. I think we should move. Okay, so I'm just going to talk about asynchronous replication mainly because we haven't talked about it before, in public, so to speak. There is a lot of capabilities that Aerospike has in terms of replicating data. We talked about how every record can have vectors. So Aerospike replicates records. So everything I'm talking about here applies to vectors, but also applies to other kinds of data types in Aerospike. Okay, key value and document. Graph is a little trickier, but that is something which probably requires one of our new features coming in, which is multi-record transactions, for you to be able to replicate things in a consistent manner. At a record level replication, vectors work great because we can rebuild the index everywhere. The basic unit of replication in Aerospike is a cluster. Everything in Aerospike within a cluster is synchronous. Across clusters is asynchronous. Okay, so that's another way to think, just to remember that. What we support in terms of asynchronous replication is essentially eventual consistency, which is another term for it is convergence. So you may not get complete consistency, some writes may overwrite other writes, but everybody will converge to the same value, all copies of the same record. So that is the first concept. The other one is we support a wide variety of asynchronous replication topologies. That's the other thing to remember here. So when you're replicating data, you can have active systems, active passive systems. There's a slight difference in color between an active cluster and a passive cluster. There's also linear kind of chains you can make for clusters, where one active cluster can feed a second cluster, a third cluster, or you can go to an active cluster going to two clusters at the same time. Now there are trade-offs. So we support all of these, and this is fairly rare. There are not that many systems which actually support this level of flexibility. In fact, I don't know of any other in the NoSQL space which does that. And this has been very, very useful again in large deployments, especially when you have disasters and you have various other rules. Like in Europe, you have GDPR and CCPA in California. There are various rules in terms of which clusters some data can be in, which geographies it can be in, which nationalities it can be in. All of that can be modeled in this. Okay? And we have support for fairly complex, like an active mesh, which is actually a very efficient way to keep A, B, C, and D, those four clusters in sync in an active manner. Can also feed a passive cluster, in this case, with cluster E. Okay? So think of this as the ability to support all of these. I'm not going to go into a whole bunch of technical details because I'd like Art to show the demo on Vector. But this is just to whet your appetite to find more information. The asynchronous replication technology, we call it XDR. This is actually an anachronistic name, mainly because XDR stands for cross data center. But we actually work across clouds, across regions, availability zones, and so on. There's nothing like a data center anymore. The name was coined in 2012. We probably should change it at some point. The important thing is there is a server process, right? Aerospike, I didn't talk about it today, but it's a distributed database. So you have multiple nodes which are running database processes on, and essentially all these are working together as a single cluster using a replication algorithm and so on inside the cluster. And then we're talking about things which are synchronizing across clusters. That's kind of what we're talking about here. So all of this is happening in a single database process, including the XDR pieces of it run in the same database process. Incoming writes can come through clients or can come through a forwarding from an XDR. I showed you a linear thing where an active cluster is feeding a passive cluster, which is feeding all the changes into another passive cluster, right? And that means the write can come into a cluster either from an end application or through this asynchronous replication process itself. And there's a whole bunch of things that we do in terms of keeping in-memory digests. Digests are nothing but the hash value of a key. Again, this is a basic Aerospike concept, which I'm not going to. But the fundamental idea is we use a last update time for a record, but also for portions of the record. And that will help us figure out what the changes are, right? Why should you ship something versus not shipping something, right? And if you can keep a last ship time for a particular link, on those links I talked about, in the database you can query the data which has changed since the last time a data has been shipped to a destination. Then you know what is the difference of data that you need to ship. So we make sure there are no holes. So data which is never, there will never be a case where you have made a change in a database and that data item somehow got missed in shipping. It may take a while to ship if the network is not connected, but eventually when the network comes back online, you're guaranteed that every change is shipped. Now, the important thing is XDR actually ships the resulting value and not individual changes. And this is something which works great for a variety of applications. Finally, the one thing I want to talk about here is there are possibilities of out of order message delivery, and we can deal with it using a certain feature that we have called bin convergence. Bin is actually another name for a column. We're a NoSQL database. We didn't want to use column to confuse people, but I'm not sure that we have stopped confusing people by using bin either. So it's one of those things where it's been 15 years old. At some point, it's hard to change a name once the database is out in production across hundreds of customers. So here's a data center 1 and data center 2. Messages can cross over. If this record has changed and the version is 1, and then the record got overwritten very fast, and that particular message showed up on the second one, since it's asynchronous, it's going to write it. And then eventually, if you didn't know to check whether this one is before 2 or not on the record, then you will overwrite it. So what happens is these two will be diverging until the next write. Then it'll all get. But then we have. So this is not convergence. So this is basically not eventual consistency. This is base inconsistency. And you don't want this, then there are many ways to solve this. And one way is with bin convergence, we will keep these timestamps and we will ship them with the record. And what you can then tell is when essentially, in this case, it's not really the same case as here, because this is the trivial case. We can just drop this particular change because it's the same record. This is passive, this is active, right? In this case, they are both active clusters. In this case, what happens is the same record is changed in both directions. If you didn't have bin convergence, you end up again with a change in 2 showing up, 2 showing up in the first cluster, change in 1 showing up in the second cluster. Now, if these updates were apart in time, then this will not happen. So if this one change had come here, and then you made the change to 2, it'll be fine. But you can't guarantee it because 2 clusters are independent. You don't know when the intermediate connection might be off for like half an hour. We don't know any of that. So if you do bin convergence, then it's possible that if we use last writer wins, if your time is going this way, this is the latest time, so this will win, this will lose. So we go end up in an eventually consistent situation. So all of those algorithms, and there's a lot more, we basically implement. I just want to conclude with this section with a very simple, with the reverse concept, which I have talked about here before, a couple of years ago. This is a synchronous active-active replication. We talked about asynchronous replication where we traded off some level of consistency in order to make things kind of move faster. Here, if you want to make this synchronous, there's also an option available. Okay, and for that, there's a trade-off. The write latencies will go up. In the asynchronous replication strategy, everything can be sub-millisecond writes and reads, whereas synchronous replication, the write latency will go up depending on how far apart these racks are from each other. This is the same cluster, so it's completely synchronous replication within the cluster. Remember, the first slide I had was synchronous within the cluster, asynchronous across clusters. This is one cluster with 3 racks and 3 copies, and it has certain advantages. And there are a lot of money transfer applications which run in this architecture on Aerospike. Okay, I'll stop there because this is an earlier topic I've covered before. And I think I would like to, I think this is my last slide. So I would, that is Art. Oh, you're hiding behind the pillar. Art will show you a cool demo.
All right.
Cool.
So basically I'm just going to show you a couple of projects that I've been working on that are integrating with the Aerospike vector search, and then so basically one is going to be a RAG, so we'll be doing retrieval augmented generation with Google's Gemma, which is their open model right now. No, Gemma. Gemini costs money. Gemma's open. So I'm using a 7B model, so there's 7 billion parameter model within this. And then we'll look at like Tim was saying, this retail kind of platform that ties together key value, vector, and graph, and all that fun stuff. So I'm going to start with this. So nothing too fancy here. But this is the RAG demo. So think like, you want to ask ChatGPT a question or whatever. You say, hey, how do I do something? Or, summarize this for me. This is kind of the same concept, right? So I'll go through the actual like pipeline of what's happening here after a moment. But like we can use Tim's example, right? So like, how do I type in with one hand? That one-handed type. How do I create a secondary index, right? So, we'll give it a shot, see what it does. And so what's actually happening right now, or has happened and then now is happening, is the very first thing, I submitted a query. How do I create a secondary index, right? And so that went through the embedding model that I'm using to generate vectors off of that as a query. And then a vector off of that as a query, and then that vector was used as the search criteria in a similarity search, right? So we take that, and I'm searching through a database of all of Aerospike's documentation. And this actually happened to pick up on our cloud offering and not our actual on-prem stuff. So it's giving you instructions for creating a secondary index on the cloud, but a lot of the same concepts. But so went through and basically grabbed the top 5 or so. So it is a 5 document, even though you see 4. It just means that it returned two chunks from one document. And I'll talk a little bit about that chunking in a moment as well. But so this query, along with the content that it pulled out of the database for these documents, is then being wrapped up into an engineered prompt to then be sent over to Google's Gemma model, which is then doing its inference and streaming back some level of response, right? And so that's the core concept of a RAG. Right, so we're just grabbing some context, engineering a prompt, and then getting that response back. So I'll show you real quick kind of what is actually happening here. If I can just try to create a new tab. As that loads. There we go. All right. So this slide right here kind of walks through the entire kind of data pipeline. So we're starting with the actual data. So what actually happened here was I just wrote a web scraper. And that web scraper is scraping our documentation, our developer hub, our blogs, our support knowledge base, basically any documentation that I could grab publicly. Taking that and then just a basic headless browser, rendering some JavaScript, some XPath queries to grab the relevant content I wanted to get from those pages. Nothing too crazy there. Each page, so every time I grab a document, I'm actually breaking it into smaller chunks, right? So this is a pretty difficult task. I didn't think it would be that difficult until I started having to do it and coming up with a way that worked well. So I wrote an incredibly complex algorithm that counts to 2,000 words and then moves on. So it's not rocket science what I'm doing here, but basically I'm trying to break these documents into smaller chunks while maintaining context
So, if you're looking at a document, you might know what you're talking about in paragraph 4 just because you're in that document. But if paragraph 4 lives on its own, I have no clue what this is actually referring to, right? So that doesn't really maintain context throughout. So I might do some kind of overlap between each of these chunks and things like that, not breaking up things like tables or code blocks or other kind of large top-level elements within a page. And so using that along with my algorithm, right, we're grabbing chunks of these documents. And so every one of those chunks is then taken with a little bit of metadata, so like title, description, and so on, and then I'm pushing that through my embedding model, right, and then producing a vector on that chunk of the document. And then I'm storing that vector along with the text and the URL for this page and some other stuff into the database, right? So that's the whole piece right there as far as how I'm acquiring this data. My embedding model, for this I used Nomic AI, so they have, it's like their 1.5 model. This one I found to be probably the best results that I saw. If you go to like the MTEB boards, they kind of fall like halfway down. So they're not really listed super high, but there were a couple key parts to it that really made it a good embedding model. So first off, it's small, right? So it's like half a gig as far as just like overall size, but it has an 8K context window. So that means that I can feed 8,000 tokens into the model to generate my embedding, right? So the other piece of this is the number of dimensions that I can create with this model is variable. So by default, it's going to create 768 dimensions on every vector that it creates. But through it's Matryoshka representation learning, it's like the Russian nesting dolls, right? I can actually cut that down, right? So I can go as low as like 64 dimensions and just kind of fine tune. The less dimensions within my vectors, the less space I need, but the less like accuracy I might have in capturing that semantic meaning and things like that. But this was a really good model I found. I tried some other models. A lot of them are small, have very, very small context windows. They'll truncate your text after like 200 words. Or I even tried just creating my own model using algorithm from Google, actually. It's DocDevec, excuse me. So WordDevec is another one they created, and then DocDevec is like another implementation of WordDevec. But it's a way to take your documents and actually train a model specifically on your documentation or whatever it is that you're trying to feed in there to create these embeddings. Turns out, after I chunked all this stuff up, it was like maybe 4,000 records, not a lot. And so, maybe times that by 1 million, and then I'd have enough data to actually train a model that could give me any sort of good results. So, training my own model was quickly out of the question. So Nomic AI worked really, really well, right? So then, of course, I'm using the Aerospike vector database for all of this. Like I said, Google Gemma. So this is the 7B instruct model. So instruct is tuned for more like chat-like applications versus just the regular 7B model. That also has an 8K context window, which again is great for passing a lot of context along with your engineered prompt. And then to get that model to fit on, so I have this running in GCP with a just one L4 GPU. And the full model at 32-bit floats was a little heavy to get into memory, so quantized down to 16-bit floats, and that got it right in that sweet spot to be able to fit fully in memory. So inference is really fast on that particular GPU, so it works really well. And then the whole application piece that you saw there, it's literally just a Python server talking to the database and then serving up like a REST API effectively to my React front end. That's it. Right? So that's the whole kind of RAG pipeline there. You might notice like I'm not using LangChain, and that's just because I didn't want to. Not to say that you shouldn't, and we're definitely going to be, we're working currently on a LangChain integration for the Aerospike vector search. It's a great drop-in kind of platform for building out these types of data pipelines, but I just wanted to try it and see what it took to kind of build all this on our own, right? And so that's kind of the RAG piece. Questions on any of that stuff? Yeah.
You only deal with the text, not for example, the document they have the screenshot, have the graph, have table.
So this is only text, correct. So if there are things like images within the documents, those are basically just glazed over. I did try to pull things like alt text or if there were captions and things like that from the images, but the images themselves were not a part of the core data that was being vectorized. So it's really just the documents themselves. Yeah.
Did you also, for the chunk size, how does the size of chunk affect the accuracy or the performance?
Yeah. So if you take just like a half a second to think about the way that I'm doing it, you'll probably quickly come to the realization that like some of my chunks might be 2,000 words long, but if I'm, let's say, looking at a chunk and literally just counting how many words are in this right now, I could be at 1,999 words inside of that chunk, and then I move to the next one, which is just going to be concatenated to the one before it, and that could already have 5,000 words in it. So then I end up with a very large chunk. So becoming kind of consistent in the size of those is going to help a lot when you're creating those vectors. And then also, yeah, like I don't want to have some records that have just massive text bins in them and then others that are really tiny, right? So that doesn't help performance-wise either.
Cut in paragraph.
Well, so that's what I was trying to avoid, was cutting things in half, like in the middle of something that might be able to carry context over. And like right now, this is still like a very much a work in progress. But you know, that's one of the, it blew my mind, like when I started doing this, you know, I had a LLM running locally and talking to it within probably like an hour. It took me over a week to come up with just a halfway okay way of chunking up the documentation. So it's a really big part of it, and there are definitely tools out there. LangChain has some of them as well that will help with that. But yeah, it's, you know, I spent a lot of time just Googling what are other people doing, right? And it's all over the place. There's nobody, not a lot of people that are doing all the same thing when it comes to that. And the problem too is it's all very different content, right? So my docs are very different than somebody else's or whatever else might be there. Yeah.
Hey, so this might sound like a random silly question, but like, did you pick A2000 because of storage capacity reasons, or?
No, actually. So I picked 2000 because a bunch of trial and error. So I actually started building this running Meta's Llama 2 70B model, but like quantized down to like 4-bit ints, so like very small compared to the full-blown model. But the Llama 2 only has a 4K context window, so it can basically accept like half the amount of tokens, right? And so you could think of like a token as like, it's like 3/4 of a word if you want just a very broad average. And so when I'm trying to push context along with my prompt to the LLM, right, all of that is becoming tokens out of the vocabulary that the LLM has. And then all of those tokens and all of the tokens that the LLM needs to generate to send back to me have to fit within that window. And so if I'm sending too much content inside of that context, very quickly run out of the ability to actually process that stuff. So the 2000 really came from when I was doing this with Llama 2. And then when I switched over to Google Gemma, I just didn't go back and revise it. But yeah, trial and error. That was what got me the least amount of seg faults. So.
My next question, sorry for finger time.
Oh, you're good.
Is there also is it adaptive learning too? The AI develop, will keep learning?
So no, so this is actually what you're kind of thinking of here is like fine tuning a model. This is like the opposite of that, right? So in fine tuning, it can be very costly. It takes a long time, right? I mean, think like Llama 2, right? And like Llama 3 is already out, and that's blowing things out of the water. But like Llama 2, 70B took 1.7 million GPU hours to train, right? That's a lot, yeah, right? So if they had 1.7 million GPUs, it took about an hour. But like even the smaller models, I think 7B was like somewhere around 187,000 GPU hours or something like that, right? So that takes a long time. Now, that's training a foundational model, right? Fine-tuning can be a lot smaller, but still, the amount of processing power it takes to be able to fine-tune these things and to continually fine-tune these things is you need to add more information, things like that. It can become pretty cost-prohibitive and just time-prohibitive. Whereas a RAG, I don't really need that because I'm providing all of that context at the time of the query, right? So I'm not training it, I'm not doing anything. I'm basically just passing it a cheat sheet and saying like, hey bud, here's the answer to my question. Just tell it to me in words that I'll understand, right? So it's really kind of a different way of interacting with the LLM without having to go through that whole process of fine tuning and all that other stuff.
Thank you.
Yeah. Cool. All right, I want to just real fast show you guys this other setup here. So this is the Aero apparel, right? So Aerospike's getting into the fashion game here. And so this is just a website as a demo to pull it all together, right? So we talked multi-model. And so this is, like right now on the homepage, you're looking at just some straight up key value secondary index queries on categories, right? So shoes, bags, wallets, and so on. If I were to come up to this search bar here, I could search something like blue Nike shoes, hit enter, right? This is a semantic search query. So I am doing semantic search on images, but with text, right? So the way that this works is when I took this data set, so this is just it's called like fashion data set out on Kaggle. This is like 44,000 different products and things like that. And so I wrote all of these products to Aerospike just as, records with all the product information, things like that. And then all of the images that come along with this, there's like one core image for each of these items. I used what's called the clip model. And so this is a model that is actually able to create or generate vectors on both text and images. And so I'm using that to create vectors on the images. And then I'm using my text query here to generate a vector on that, right, the query, and then doing similarity search between what my text gets and the images that I have within the database, right? So that's pulling up like the top 20 results is what I have this set up for.
Specifically, you said you were able to get images. Were you able to get images on this website?
So this is a different model, right? So like what Tim was talking about before, where it's going to be very like use case dependent. So this is a totally different model to be able to generate these and very specific to this task, right? So I'm doing some very, very kind of simple image searching through this. Now, if I click on a product, right, I can go to the products page and you can see product information. So the top half of what you see here, right, this is all key value. It's just a quick, hey, this is the product ID, go grab it from the database. Then I come down here and I can see similar items. This is another semantic search, but instead of text, I'm actually taking the vector that was generated for this particular product, and then I'm using that as my search criteria to grab like the top 10 similar items, right? But then I have this also bought down at the bottom here. And this is your graph, right? So we have customers in a graph with our products, and basically what I'm doing is I'm traversing that graph, so I'm saying, hey, I want to find everybody who bought this, so the product that we're on the current page for, and I want to look at what they have also bought. And then I'm going to aggregate what all of the people that bought this also bought, and then I'm going to grab the top, say, 10 items from that, and I'm going to return them back to you as, hey, people who bought this also bought that, right? It's just a simple kind of recommendation engine query. Again, this is a work in progress, but it's very simple to tie all these things together. And I'm running all of this in one Aerospike database. Just one database, right? And doing my graph queries, doing my semantic search, doing my key value, all of that, one database. And so that's really kind of like the power of this multi-model setup that we've got. Yeah?
Do you actually support the SQL queries actually to the, for example, the size of the shoes and blue, like you do the embedded, the vector search?
So none of that yet, right? So basically what you're returning here is just a giant document for this product, right? So it's just listing out, these are the available sizes, these are the available images to be able to, go and look and see, what this product looks like, all of this, right? So this is just a simple key value lookup of a document effectively, right? But if you wanted to, you could take something like the description, right? And you could run that through, let's say, the Nomic AI embedding model, generate embeddings on that, and then have a second index that is working on, searching vectors within that space. So.
The only thing I would add is you can build secondary indexes in Aerospike. So you could build it on shoe size or whatever other things. Mm-hmm. You could use that query to get the list of objects and do everything that I talked about.
Yeah. So like here I can do another key value but secondary index query on, let's do like sports stuff, right? So here's things that fit into the sports category or whatever.
Yeah,
right.
Because previously they discussed the fluid size and land area, you gotta say if we have multiple columns, you actually could do the embedded for all columns. So that would be great if you actually could. I don't have to create the index, so I could credit this column and the embedding.
Yeah, so that's something that is like to be on its way, right? So they're actively figuring out kind of what the best way to attack that, secondary index. And then how do I generate that? It's that conversation we were having just last week in the office, trying to identify kind of some of the ways that we can come up with this. Because a big part of when I build these things or why I build these things is also to figure out like what sucks, right? What are the problems that I'm running into that would be really great that I'm sure our users are going to run into? And so this is a fun kind of way to identify needs, right, within our product, on top of customers.
So it only deals with like the items, doesn't deal with like the user's information at all or something?
So right now there's no user profile. So we have users in the database, but we haven't really connected a profile piece to it yet. So like I said, we're going to be building out like a shopping cart and the user profile store and other types of recommendation engines and potentially other types of semantic search. And all of the code actually behind this will be made public. And the goal is for people to be able to come in here and kind of pick and pull modules out of it. Like, I want to know how to do this in Aerospike. Or you just take the whole thing as a platform and mess around with it on your own. So,
is there like a variable that it's not random, but is there like something like determines like how popular an item is versus another? And that's kind of a specific question, sorry.
In here, no, it's all random. But I mean, one of the great things about like these graph queries and things like that is you could probably very quickly find that out, right? And so identifying what are the more popular items, and then why are they more popular, and tracking that kind of stuff.
Sorry, I just thought because I think Amazon does similar to that, so I'll be going into clues. Sorry.
Yeah, I mean, that's pretty much there already. It's just writing the queries, right? So, and doing the analysis on the data. Cool. I think we're pretty much right at time, almost.
5 minutes left.
Oh, cool.
So I guess the last thing we need to do is raffle off the rocket. Yeah. So hopefully this has been of interest. Has everyone who wants to win the rocket registered? Anyone need to register?
Anyone need the card to register? You do. Okay. So you have about 60 seconds to register.
Green meeting, thanks.
Sorry?
Oh, green meeting.
Oh, thank you. I appreciate everyone paying attention. No one fell asleep. I was very impressed. I didn't expect anyone to fall asleep in after Srini sections, but mine, it was touch and go on a few people. Okay. Anyone who, we're still registering? We've got a couple of people who are registering. So we're going to do this live. We'll show a website which will have this button. Everyone registered.
While the last people are registering, though, please, anyone have a question? You can take one more, so we're not just sitting
They're
there.
going to ask if you're going to give this slideshow out, are you?
If they are you guys giving out the slideshow after? We're going to publish the video from the event, which will include everything on the screen. But if you specifically want the PowerPoint,
we're very happy to give it out. We'll work with Eric and work out the right way of distributing it for people who want it.
Yeah, on the website, right?
What?
On the YouTube channel, right, for you guys?
We'll get it somehow. I'm not sure exactly. We'll make sure it's available and it's going to be emailed out through the
website.
Thank you.
Anyone have a last question before we raffle off the rocket? Nobody? Yeah, yes.
I have a question about the clustering stuff that you said you talked about 2 years ago. But is there, the difference between, if I remember your slide right, the top left is sort of active passive, the bottom right is active mesh passive.
Right.
What's the difference there because the cluster looks like an active mesh.
Yeah. So we used to support circular kind of systems, but that created problems because you don't know when to stop. So you're doing an infinite loop at some point. I mean, we tried our various techniques. So eventually we ended up with active-active ended up being a mesh. That way you know that if something is coming from XDR to a cluster, you don't have to ship it. So but you have a linear active-passive link, then you know to ship it. The problem is you have to separate out. I mean, the client does send a bit. If it is an XDR client, it will send a bit. The server will know it's an XDR request. But if you're doing a cycle, so that's why we went to meshes based on experience. This whole technology has been around for since 2012. We rewrote everything in 2019, I think. So it was in production for 7 years, and then it's been in production in this next version for 5 years. So it's a lot of. We never talked about the asynchronous application things much for some reason. I don't know why. But the core database, we've talked about clustering within the single cluster, how the nodes talk to each other. That's itself a hard problem because you want to maintain strong consistency, not lose data, and so on. And then what we are finding, and what we found actually, more like our customers discovered it, is that when you have asynchronous application with Aerospike, we are able to keep up with the heavy write throughput and read throughput. It's typically write throughput for replication. It could be like hundreds of thousands to millions of writes per second. We can keep up. And that's a divide and conquer algorithm. I didn't go into the details. The core Aerospike database has a 4K partition list. So it's a divide and conquer algorithm. So we can run with 4,096 parallel shipping links at the same time. So even if we ship a few hundred with 4,000, I mean, that's like getting close to a million or so. Yeah. So.
Hang on to that. All right, that's all the time we have for questions. Before we raffle off this rocket, I want to give a great big thank you to Srini, Tim, and Art. you guys ready to get the raffle up?
I'm not sure.
You gotta figure out who's winning.
We're doing this live, so you can see that we're not making this up.
Yeah.
Going live.
We had 27 lines, is it
Yep,
correct?
that's about right. Give it a title. Just put MIC. Something.
I should pick the blank line.
Hopefully I eliminated them.
Drum roll, drum roll.
Is it gonna show
Yeah,
the
just
wheel?
just say confirm.
It's just like.
All right, and start. All right, drum roll.
All right. Hey. 5, 4, 3, 2. Happy New Year.
Wait. What?
You didn't exclude the blank line. There's a tick box for ignore the first line. Let's do this again.
Let's try.
Yeah,
to
yeah.
replace.
My bad. I take ownership. Yeah.
You just want to have the one.
Okay, so that was like a.
That was anticlimactic.
There we go.
Elvis.
Who's Elvis?
Who's Elvis?
Elvis.
Me.
All right.
Okay.
You want a Saturn V rocket, man?
Congratulations. Oh, you got to take a photo. Take a photo. You're supposed to take a photo. Okay. Hold on.
You just won that, yeah?
No. Post for a photo.
Yeah.
Post for a photo.
Tim's doing it.
All right, guys, there is a little more food outside. Feel free to take it all home with you. We're not going to keep it. Thank you all for coming.